do that. Let me just start with an example. So this is a dumb example. So say I have logical 0 is say I'm using the repetition code. Okay. It's not a quantum code, but it's just a 3 classical code. So now I have my encoded state is going to be alpha 0, 0, 0 plus beta 1, 1, 1. It's not resilient against Z errors. It hopefully is resilient against X errors. So when I want to correct this code, I don't want to measure any of these qubits because that would collapse the superposition. So instead what you do is you measure the stabilizers. So I'll prepare a 0 here, and I'll do CNOT gates like this. And then I'll measure. So I'm measuring the parity of the first 2 qubits. Hopefully it's even. Then I do the same thing, or I'll do it here. I don't know. Qubits 1 and 3, whatever. 0, 1. So now I'm measuring the parity of qubits 1 and 3. Together, this should be enough information to tell me where any single X fault has occurred. So if there's no faults, you just measure 0 and you measure 0. If there's an X fault here, you measure 1, 1. Next fault here, you measure 1, 0. Next fault here just measures 0, 1. So those 3 X faults are given by the 3 non-trivial syndromes that you would observe. So the correction rules are. So these are the rules. What you'd say. So you say for every syndrome, 0, 0, 0, 1, 1, 0, 1, 1. That's every measured syndrome. This is the correction you apply. Identity. So 0, 1. 0, 1 means only this one was triggered, so that's X3. 1, 0 means you have X2. 1, 1 is X1. All right, so in this example. All right, so but unfortunately this is not fault tolerant still. And then the reason is because you could have, I mean, we're not just worried about X errors on the input, we're worried about what if maybe there's no error here, but an X error occurs in the middle. So for example, if an X error occurs here, on the first qubit in between, the syndrome we measure is going to be 0, because we haven't seen anything yet, 1, because it anti-commutes with this stabilizer, with this parity check. So you measure 0, 1, and you apply correction X3, and X star in qubit 1, I apply X3, so now I have X1, X3, which is a logical error up to X2. I mean, it's a way 2 error from a single fault, so that's bad. So instead what you do, actually I don't know what you do, but maybe, let's see if we can fix it. Probably, maybe. Let's just do something else. I don't know. Let's try like that. Okay. So now I'm measuring 3 syndrome qubits and 3 syndrome bits, and the idea is to, well, let's see what happens. All right, so the third one's just the same as the first one. Otherwise, don't do anything. And let's see if this works. So what I want to say is that if there's an internal fault like here, okay, so if there's an internal fault here, the first would disagree with the second. And so it's not one of these cases, and so you don't do anything. And it's fine, you don't have to do anything because it's a weight 1 error. Yeah. I don't know. So you can do case checking and try to see if this works. I think it works. Probably.
Does that problem like channel 1, like if an error occurs between the second and third measurements?
Right. So here again we run into sort of the issue of what the right definition. What are we aiming for when we say fault tolerance? When we talk about state preparation, we said a single fault should cause a most weight 1 error. Here it's different, maybe. I mean, okay, so again, we certainly want that to be true. We want a single fault to cause a most weight 1 error, because 2 would be bad. but we want something stronger. We want to say that this circuit with these correction rules, it should make the circuit better. It should do error correction. And so what we say is that, okay, so let me write out a definition. So I'll say one error fault tolerant error correction. So one error fault tolerant, one fault tolerant error correction. What it should do is see if this makes sense. Any one fault